It's a pleasure for me to introduce Olivier Legal in presence here to give a talk, to give a blackboard talk with the title Dichotomy, Interlacement versus Hardy Indefinable Ordinary Differential Equations.
Thank you. So I first want to thank the. Is it okay for the microphone? Yeah, okay. So yes, so I want to thank the organizer to invite me and to give me the pleasure to give my first talk in presence since the pandemic. So I hope I'm not too rusty. Okay, so I will talk about dichotomy. So interlacement versus RD for definable ODEs. Okay, so well, yes, first it's a joint work with Mikhail Matuszynski and Fernando Sanz. Okay. And so it's a result about the relative behavior of two trajectories of definable definable vector field in R3. Okay. So I don't assume everyone is familiar with this kind of thing. So I will start by a kind of introduction where I give some examples of some analytic examples, let's say, and some motivation with the recalls of what is known already. So I start with this for motivation and examples. Okay, so all my examples are based on the Euler differential equations, well known. So I just recall you what I need. So Euler differential equation. So it's the differential equation x squared y prime equals y minus x, and so. So in this, so it's an example of a saddle node situation. So here, yeah, I want to draw the phase portrait here with x and y, and so you see if you write it as a vector field, so the trajectories are the trajectories of the vector field xi, which is x squared dx. Plus y minus x dy. So you see you have a well 0, which is a singular point. You have a linear part which has so here an eigen yes it has an eigenvalue 0 here and an eigenvalue well here eigenvalue 1, I think. Yes, and I can value 1 in the direction x equal y, and so you have an unstable manifold here, which is given by it's given it's x equals 0, and you have a formal central manifold. That you can get by trying to solve this differential equation, well, y in terms of x formally. So if you try to do this, you get some y of x. So you see to go at 0 to 0 here, you need y to start with an x. Okay. Then this x in y prime gives you 1, so you got x squared here. So y should get an x square. And this x square, when you calculate the derivative, you got 2x. You plug it in, you get 2x cubed, which comes here. That's 2x cubed. And you see, each time you will calculate the derivative, you will have the exponent false, and then you will end up with some factorial n, xn plus 1 plus and so on. Okay, so this is this is a divergent formal series, and if you look at the dynamic along the formal central manifold, you have a dynamic which is like this. Okay? And so all trajectories do something like this. And here you have all trajectories which arrive, which go out from the origin with the same asymptotic development, which is this one. Okay, so this what happened on the right-hand side here is the part that I'm interested in is an example of what Cano, Moussu, and Sans. Cano, Moussu, Sans called a pencil of trajectories. Pencil. So formally, what it is, a pencil of trajectories, it's the family of all trajectories that you cannot separate by punctual blow-ups. So all trajectories that cannot be separated by punctual blow-up. And well, if you're not comfortable with this definition, for my talk, you can just think that they all have the same expansion, and it's okay for my talk, even if it's not completely equal. So here, at least in the case I will consider, it means having the same formal development. Okay, so what we study are the finiteness properties of such trajectories, and you have two questions that you can have in mind. Is given one trajectory of a vector field, what are its finiteness properties? The best being it is minimal, polynomially bounded, all you want. And the second question is, what is the relative behavior between two trajectories? So here, if you take two, the question is, does they both belong, let's say, let's be generous, do they both belong to the same minimal structure or not? So in dimension 2, actually, since well, trajectories of vector field have codimension 1, you can consider Pfaffian leaf instead of trajectories, and then everything is either oscillating or Pfaffian, and so there is no question in dimension 2. In dimension 2 here, for instance, in this example, we know that any trajectory here is Pfaffian, so they all have the best finiteness property and the best compatibility property. Okay, so let's go to dimension 3. So in R3, well, now we don't have this equality between leaves and trajectories, and so I will just make some construction with this example to give you some kind of phenomenon that can happen. So my first example is the following. So sorry, the vector field is so again x squared dx plus yes, y minus x dy plus, and so I took 1/2 of z minus x dz. So okay, if you just look at the differential equation which comes with this is x squared y prime z prime equal. So you got here y minus x, here 1/2 of z minus x. So you see it's almost 2 copies of the first one. Okay, so you have here the same equation, and here the same, except you have 1/2 here. So again, what you will get. So here I have x, y, and z. And what we get again a formal solution, which is well, y z hat. So for y you get the same. So it's the sum of factorial n x to the n plus 1. And for z, because of this factor, you get a 2 to the n. Sum of factorial n 2 to the n plus 1 x n plus 1. And so you have your formal curve here. Okay. And if you want to understand the dynamic, so here again you have this. So this is a formal central manifold. You have one eigenvalue on the z, which is 1/2 here. Another one on the y-axis, which is 1. Okay, and if you want to understand how works the trajectories, you can look at the difference. You see here you can express y and z in terms of x, and you can consider the difference of 2 solutions. Okay, so here you have your trajectories; they are all asymptotic to the same formal curves. And if you consider gamma and delta, delta minus gamma. So here gamma and delta are two solutions. Okay, and if you consider the difference, you get, well, gamma minus delta satisfies just the linear part here. It satisfies the system x squared y prime z prime equals y 1/2 of z. Okay, and so the difference delta minus gamma will be some. So you have 2 flat exponential. You have exponential k exponential minus 1 over x, and k prime exponential minus 1 over 2x. Okay, so you have this flat exponential. Yeah. Okay. So in this case, of course, if we ask for the finiteness properties, everything is there is a bias because I just have copied two-dimensional system, but it could be more general, of course. And I give you another example, which is on the same ideas, but with a very different behavior. So I consider now the vector field given by x squared dx plus y minus z minus x dy plus y plus z dz. So the corresponding differential equation, it's of the same nature. So it's x squared y prime z prime, which will be, so you have y minus z minus x for y, and for z you have y plus z. Voilà. So actually the way I produce it, I just consider w to be y plus iz. And if I do this, w satisfies the differential equation x squared w prime is 1 plus I y w minus x. So you recover almost the same differential equation here, except you have this complex number here. Okay, and so you have a formal solution for w, which is the sum of the so still factorial n x n plus 1 over 1 plus I to the n plus 1. Okay, and so if you want the asymptotic behavior of y and z, you just take the real part and imaginary part of this one. Okay. So if I make the picture, just formally you have the same kind of situation as this. So you have this formal central manifold here. You have x and y there, x, y, and z here. In this plane, you see that you have a complex eigenvalue, so you have spirals. Okay, and if you want to understand what happened for the trajectories which are asymptotic to this formal curve, again you can consider the difference. This one. So well, yes, if I consider again, so delta minus gamma, where delta and gamma are two solutions of this, you will end up, well, with the same differential equation except this point, and then you get two flat exponential with a complex argument inside, and so this will be something like sorry. Okay, e to the -1 over x. Okay, so this one is the one which is there, and times some cosine of -1 over x plus phi of -1 over x plus phi. Okay, so you have two parameters that parameterize all differences. And you have so this flat exponential, and here something that turns infinitely many times as x goes to 0. Okay, so if you want to see what happened here, you have in some way you have a flat cone around the formal curve, if I can say. Okay, and the trajectories, the spiral along this cone. Okay. Okay, so and well, the difference of any two of them spirals also. Okay. Okay, so these are for the examples, and so in fact, what happened in the analytic situation? So this is a result of so let's say what is known. So it's of Cano, Monsu, and Sans. So it's in dimension 3, we have analytic vector field, and the one result is that a pencil of trajectories is either separated or interlaced. And so what does this mean? So separated is this situation mostly. And what it means that you can separate any two trajectories by a projection. So here, for instance, you take two trajectories. Okay, so these two, for instance, you project it on the XY plane, and you will get two projections which have empty intersection. Okay. So this means that for all gamma delta, which are solutions, so on, there exists a projection, a submersion for R3 to R2, such that P of gamma intersected with P of delta is empty, let's say, near 0, okay, as a germ. And or, so either it is separated or it is interlaced. And interlaced, it's exactly this situation. And this, what does this mean? It means that you have this interlacement of any two solutions. Okay, you get to something that looks like this. Okay, and one way to say that, so I'm changing a little bit the original definition because, but it's equivalent. So here, everybody is parameterized by x, okay, and I consider so delta of x minus gamma of x, and I consider the angle between this difference and a fixed vector field, fixed vector. Sorry. Okay, so so what does this mean? It means that for all gamma and delta, which are solution, if so, theta is theta of x is so it's a continuous angle which gives you so theta of x. Sorry, so cos such that cos theta sine theta. This is gamma minus delta minus delta gamma over delta minus gamma. Okay, so theta is the angle done with the horizontal vector. So if theta is continuous and satisfies this, then theta of x goes to plus infinity as x goes to 0, or theta of x goes to minus infinity as x goes to 0. Okay, so you have this this dichotomy. Okay. In general, for pencils of trajectories in the analytic situation. Okay, now what is known for my first question? This means what are the finiteness properties and finiteness properties of pairs of trajectories. So we consider two cases again. So if the pencil is interlaced, there can be two possibilities again. The first one is, so it's a very weak finiteness properties. So a trajectory, well, let's say for one trajectory, so gamma is oscillating. So what does this mean, oscillating here? So it's here, since the vector field is analytic, it's all, we are talking of oscillation with respect to analytic set. So it means that there exists S, an analytic surface, well, analytic set, let's say, such that gamma, well, the support of gamma intersected with S has infinitely many components. So this is exactly what happens here for the difference of two trajectories in this case. Okay, you have, for instance, so the solutions are over there. If you take, let's say, y equals 0, you have a trajectory which intersects the horizontal plane infinitely many times. Okay, and in this case, the axis is analytic. Okay, so this means that the formal curve we had here was convergent. Okay, or gamma is non-oscillating. Okay. And in this case, actually, gamma is ominimal. So we have the best result possible. Then gamma is ominimal. So this can be so for many cases it is done by Rollin, Speisiger, sorry, Rollin Sandschlefke. Okay, and for the general case, it is done by Le Gall Sandschlefke. Okay, and of course, so here I'm talking about the finiteness property of one trajectory, But of course, if you take two of them, since they are they turn around each other infinitely many times, you have no hope to get anything. Okay, so here we can say the question is over for a pair of solutions. Okay, and now comes the other part. So if the pencil is separated. Now, very few is known. So one thing that can be said is that any gamma is non-oscillating. Okay, so that's the general finiteness result we have. Oh, yes, here I want to say something. So saying that a trajectory is non-oscillating. So you see, it means that for any analytic surface, the intersection has finitely many components. And so if S is given by f equals 0, okay, it means that if you calculate f over gamma, okay, it will have a sign. Okay, for small x, it will be either 0, so it means it is included in the surface, or it is out, so it's either positive or negative. Okay, so any analytic function composed with gamma will have a sign, and it's not hard to see that if you consider all analytic functions evaluated over gamma, you get something that is closed by derivation. Because if you calculate the derivation, you will have the derivative of gamma, which appears, but the derivative of gamma is, well, gamma satisfies the analytic differential equation, so the derivative of gamma is analytic function in terms of gamma, okay? So if you consider O of gamma, so by this I mean all analytic function evaluated over gamma, okay? You will get, clearly a ring that is closed under derivation. And what I just said, that anyone has a sign, means that if you are not 0, you have an inverse. So this is what is called the Hardy field. Okay, so non-oscillating, it is equivalent to consider this ring of function and say that this is a Hardy field. Okay, and then. Is there anything else I wanted to say in this case? Okay, no, and now so well, in this situation actually we don't know if gamma is O minimal. This is any gamma is O minimal, so this is an open question. So there are some cases that can be solved, but we have nothing general. And for the relative behavior of two trajectories, you see that in this situation, it is the situation where we have some hope that we have something. And for gamma and delta together, of course, we don't know more. Okay. Okay. So. Now I think I can explain what were our actual initial motivation for our work. So the first thing we wanted to understand is this. Okay, this means you take two trajectories. What kind of compatibility can you have in the separated situation? Okay. Of course, since we already don't know if one trajectory is minimal, the best result we can hope is not that they are both minimal. Okay. Okay. So what we can hope here is, you see, you have a kind of you have an equivalence between non-oscillating and being a Hardy field, and here, for two trajectories, you could hope something analogous. So this means, well, do we have that? This means that if you consider all analytic functions, so here you have to, well, over gamma and delta, yeah, you could ask whether this is a Hardy field or not. Okay, so it's weaker than being minimal, but still it's okay. Okay, and so that's one of things that we managed to prove. So that's the first thing. So it's we we understand a bit better the separated case. And the other thing is, well, the argument here, we have the feeling that it's something a bit general. Well, this dichotomy should be more or less general, and so we want to generalize it not only for analytic vector field, but for well, for some ominimal structure, at least polynomially bounded. So we need this polynomially bounded to give a meaning to this flatness condition of being in the same pencil. Okay, so that's more or less what we do. So okay. So let me pass to the second. So I will explain what are the main results. Okay, so the data now are so an ominimal vector field, which is definable in some ominimal structure that is polynomially bounded. So let's say it. We fix an ominimal minimal expansion of okay, that is polynomially bounded, and so each time I say definable, I mean definable in this structure which is fixed, and so we consider psi vector field definable vector field. So it's C1 on some open set U. Well, I want to fix the point here, so it will be 0, and so I ask 0 to be in the closure of U. Okay, and I consider trajectories of C inside of U. So of course, I suppose I have some. So I have gamma and delta trajectories of C inside U, and I want these two trajectories to go to 0 as omega limit point, let's say. So here T is the time of the vector field, okay, as T goes to infinity. So here comes some difficulties. Why? So what we want to do is, first, yes, first we want to generalize this kind of idea. So we want to a conclusion where we say gamma and delta are either separated or interlaced. Okay, but we need to take, of course, gamma and delta in the same pencil. Here, in a general ominimal structure, well, we don't have a formal series. Point blowing ups are not well adapted if we have real power functions, and so we end up by saying that two trajectories are in the same pencil if they have a flat contact. But if you think of flat contact comes with some coordinates. You say having flat contact means it's smaller than some x to the n for all n, but x is some given coordinate. Okay, and actually it happens that sometimes the flat contact might depend on the coordinates system. So it's a bad thing. So this is the first thing we have to deal with. And another thing is, again, with this coordinate problem, we want this object, well, here we will replace analytic function by a definable function, of course. Definable function evaluated on gamma and delta to be a Hardy field. So again, we need a coordinate. So let me recall, a Hardy field is a field of a function of one variable. So you have one variable somewhere. So we need one given variable in order to parameterize the two trajectories, okay, and get well, a field of germ of one variable function. Okay, so we need this system of coordinate, and it's not completely obvious. Well, you can always take a system of a definable system of coordinate as long as gamma or delta is non-oscillating, but in order to have a robust notion of what is it to have flat contact, or to even well, to be in the same pencil or not, you need a bit more. And so yes, so, okay. Let us say I ask you to believe me that the part where we deal with the system of coordinates is in fact harder than the rest of the result. But so I skip this part, okay? I just present you everything in the reduced situation. So in the reduced situation, we have a coordinate system, and everything is parameterized by one coordinate, and we have we need some good condition on this coordinate with respect to one trajectory. So I will explain this. Sorry, I should start there. So I go to the reduced situation. So this means, so here we have a system of coordinates. It's y1, y2 of definable coordinate. And gamma and delta are both parameterized by x. X, so gamma 1 of x, gamma 2 of x. So this, I will call it gamma of x. Okay, and delta is x, delta 1 of x, delta 2 of x. So I give a definition of a good property that has certain coordinates. Okay, and so and that is let's say a necessary condition to be sure that this notion of flat contact or not does not depend on the choice of the chart. Okay, so we say that gamma has regular separation if so for all f from R3 to R, it is definable. So either f composed with x gamma of x is 0, okay, or there exists an n such that f of x gamma of x is larger than x to the n. So of course this two must be understood as x is close enough to 0. Okay, so either you vanish or you're larger than some power. Okay, so just to give a hint of what is this definition in the analytic case. So in the analytic case here, we have a formal curve. And what would happen is that this formal curve is included in an analytic surface. Okay, this could happen. You have S, which is analytic, which contains a formal curve. And so, well, you have your pencil of trajectories. So you have all trajectories that goes to 0. Yes? So here it's just to give a hint of what this means in the analytic situation. So this formal curve is the axis of the pencil. Okay, so here I go back to the examples if you want. Yeah. Okay. So X. Okay, so here you have two kinds of trajectories. You have some trajectories which are included for true in the surface, okay, and some which are not included in the surface, okay. Okay, and so the one which have this regular separation properties are the one which are truly included in the surface. So this should be understood, at least in the analytic situation, as an equality between the formal transcendence degree and the geometrical transcendence degree. Okay, if you satisfy some analytic equation, you should satisfy formally. You should satisfy it for true. Okay. Okay. So this means, well, yes, equality of the formal in geometrical transcendence degree. Because well, let's say this is the idea of what is this object. Okay, and now I can also define. So what it is to have flat contact. So here it's easy because I have a good coordinate. Okay, so I say that gamma and delta have flat contact if well, for all n, gamma minus delta norm is smaller than x to the n for x sufficiently small. Okay. So it happens that this condition well, ensures that the flat contact does not depend on the chart and things like this. Okay, and so now to state my theorem. So now I have the hypothesis. So I want one trajectory to be to have regular separation, and the other to have flat contact to the first one. Okay, and my conclusion should be, so for my conclusion, I should have either the interlacement, okay, here, or the separation in the strong way. This means that they are co-hardy, and so I need two more definitions. So for the interlacement, in fact, the definition is over there, and it works. So it's the angle theta goes to plus or minus infinity. Okay, so that's the same definition. And for my field here, I consider, so I call field well, a ring of definable function over gamma delta. So this will be the set, so I wrote it f of gamma delta, and this is a set of all functions of the form some h of x, gamma 1 of x, gamma 2 of x, delta 1 of x, delta 2 of x. Okay, when h R5 to R is definable. Okay. Okay, so now I can state the result, the theorem. So Matuszynski France. So we let gamma delta with well, gamma has regular separation. Okay, delta has flat contact with gamma, and the conclusion then is gamma and delta are interlaced. Or, well, this ring f of gamma delta is a Hardy field. Okay. Oh. Yes, it stopped at 20. Okay. So what can I say in 5 minutes? Okay. Yes. Well, maybe I can. So you see, it's what I just announced before. So if you go back to the analytic situation, so you can in particular apply this this theorem in the analytic situation. So you see that we recover, of course, this dichotomy, but we got something better for the separated situation, since we got a Hardy field here, and it's way better than having one projection which separates the two. And in particular, we can prove with this that in this situation, any projection, okay, separate the two trajectories. Okay, so that's one thing. And well, the other good thing is that well, we generalize the result to any polynomially bounded minimal structure. Yeah. Okay. Maybe I stop there. Yeah. So, yeah.
Thank you very much for the talk. Are there any questions in the audience or online? So maybe I start with a question on my own. So in this non-oscillating case, does the trajectory have a tangent at the origin?
Yes. Actually, non-oscillating here implies that you have iterated tangents. So
then you have a tangent.
Iterated even.
Okay.
So,
okay.
Yeah.
Okay.
Yeah.
Mm-hmm. And you said at the end that this theorem generalizes this, but the setting is a little bit different, because here you have definable, and here you have analytic, and not necessarily definable Hardy field, because analytic functions.
Yes. Mm-hmm. Yes, of course. So here, yes, you can replace analytic functions by sub-analytic function if you want.
Okay.
In the analytic case, it was already known because, well, it's something particular of the dimension tree. It's the fact that if gamma is oscillating, then the axis is analytic. So here, if you start with some gamma, let's say you could have the fact that gamma is non-oscillating with respect to analytic set, but oscillating with respect to sub-analytic set. Okay. But if this happens by transforming your sub-analytic set to an analytic set by blowing ups, you will recover upstairs something that is oscillating with respect to analytic set. Then you have an axis which is analytic. Mm-hmm. And then when you go down, since there is no sub-analytic curve, you have only analytic curves. Okay, so you will finish with an analytic axis, and then you have oscillation with respect to something that is analytic. So here, the gain, what we gain by replacing analytic function by sub-analytic function, well, it was already known in this situation.
Okay.
I can say something. Here you have the hypothesis that one of the trajectory has a regular separation.
Yes.
But in the general case, you can have a pencil of trajectory which is separated where no trajectory inside has this property.
Okay. So
all of them are flat with respect to an analytic curve. So,
Okay. Yeah.
so there are no trajectory. So in that case, we don't, for the moment, we don't know nothing about Hardy fields or two trajectories.
Okay. Yeah. Well, on the other side,
Yeah.
except for the case that you mentioned that well, when the axis is made of singular point of the vector field, we managed to prove that any other pencil always have a trajectory that is separated, and in fact, well, there is a subanalytic set which contains all trajectories which have these properties of having regular separations. Right? Yes. Yeah.
Thank you. Are there other questions? Chris?
Yeah, I just want to make sure I'm reading this properly. In your theorem, you're only assuming C1?
Yes.
Okay.
Other questions? Clarifications? Jean-Philippe?
Yeah, so in the case of a separated pencil,
Yeah.
here, so when you ask the question, gamma is homonomial, does it mean that you don't know anything, or that do you have counter examples?
No. So here, so the question is open. Okay. Well, you know very well that the same question in dimension 5 fall because you gave a counterexample, but in dimension 3 and 4 we don't know. Okay, and in dimension 3 there are some results in particular case where any trajectories are minimal actually. Yeah. So
yeah. You don't have examples where it is not.
Yeah, exactly. Okay. The question is still open in dimension 3 and 4.
Dimension.
Yeah.
Thank you. More questions? Maybe online? Seems not to be the